Welcome once again to my channel. I am Dr. K. In this video I want to show you how to identify the stereogenic centers in some ringed compounds. So the method for identifying the stereogenic centers in ring compounds is different from that you can use to identify the stereogenic centers in straight chain compounds. So I'll be guiding you through the principle for that. Alright, so when we are talking of stereogenic centers, what we are simply talking about is when carbon is attached to 4 different substances. So one carbon, when it's attached to 4 different substances, then you talk of the carbon is the stereogenic center. Yeah. So but when we are dealing with ringed compounds, so there are like certain conditions that must be fulfilled before you can talk, okay, this is stereogenic center or not. Alright, so now what I would like you to notice is that a carbon in a ringed compound, like so I have a lot of ring compounds before me now, right here. So this is wherever you see the white board, that's where I'm pointing to at the moment. So this is 2-cyclopentene 1-ol. This is 3-cyclopentene 1-ol. This is 1,1,2-trimethylcyclobutane. So this is limonene, and this 1,13-trimethylcyclobutane. So these are ringed compounds, example of ring compounds. Alright, now in a ring compound, a carbon atom can be a stereogenic center. Now these are the conditions that must be fulfilled. Now the first thing is that it has to have 2 different substances as substituents. So what am I saying? In a sense, it could be a methyl group or an alcohol group. So that's one of the conditions. Or let's say it bears it bears an aldehyde group and maybe an hydrogen. So you understand, it has to bear 2 different substances. That's the first condition. And also another condition is that the part traced around the ring from that carbon is different from that traced in the other. So like when you are tracing the parts around that carbon that is the stereogenic center, so the part has to be different when you are tracing it in different directions. Alright, so let's go. I will illustrate. So you actually got the first one, but the second point I made you might not really get. So I will explain with the examples I have here before me. Alright, so let's study. The first one we have here is 2-cyclopentene 1-ol. Now look at them, 2-cyclopentene 1-ol. The 2 there is showing that, so you can see pentene, so it shows that it has an alkene. Now the 2 there is showing that the double bond is present at the second carbon. So can you see? That's here, second carbon here. Double bond is present there. Now 2-cyclopentene 1-ol. They now said we should identify the stereogenic center there. That's if it is there. Alright. Now, don't forget from the level I said that the dark carbon atom must be attached to 2 different substances. Now let us look at this first carbon here, carbon 1. I was the one that numbered it here, carbon 1. You can see that it is attached to hydrogen and alcohol, 2 different substances. Can you see that? Alright. Now, another thing is that the part traced around that carbon must be different from that traced in the other. Okay, now let's trace the part. So let's take 1, 2. So you can see that our double bond is at the second carbon. 2, 3, 4, 5. So that's one. This is a part traced around it. Okay, now let's trace it to the other side. 1, 2, 3, 4, 5. So can you see that? Now if we go by that, you can see that when we are tracing here, we have our double bond at the second carbon when we are tracing towards the direction. So towards here, that's the towards the second and the anticlockwise. We have our carbon on our double bond at the second carbon. When we're tracing here now, 1, 2, 3, 4, you can see that our double bond is on the 4th carbon. Are you getting what I'm saying? So you can see that the parts are different. So the parts are so as a result of that, so you can say it has its stereogenic center because the parts are different. Okay, now 3-cyclopentene 1-ol will help us to understand better. Okay, let us trace it. 1, 2, 3. You can see that we have our double bond at the 3rd carbon, Abi, right? So that's why you have so then we have 4, 5. You can see that now. So we've traced that. Yeah, so you can see that. Now let's follow the other part. So this is our stereogenic center, don't forget. So 1, 2. So that's why I named 5 equals to 2. So that's when you are numbering to the other side. So you know 5 at one side is 2 on the other side. That's why it's 5 equals to no 1, 2, 3. So you can see that we still have our double bond at the second carbon. So as a result of that, we can see that the path traced around are the same. Now because the paths traced around are the same, so it shows us that it doesn't have a stereogenic center. It doesn't have a stereogenic center. So that's the condition for that. All right. So now let's go. The third one I'm naming here is identifying the stereogenic center. That's if it's present is 1,1,2 trimethyl cyclobutane. 1,1,2 trimethyl cyclobutane. You can see 1,1 is showing that on the first carbon we have methyl. We have 2 methyl on the first carbon. Then 2. That means on the second carbon we have another methyl. So making 3 methyl. That's why you have trimethyl. All right. So now let's trace. Now the possible stereogenic center. Okay, let's look at this first one now. It cannot be a stereogenic center. Why? Because it has the same substance. That's methyl and methyl. You can see that. So these lines you are seeing, that's for methyl, representing methyl. So it couldn't have been a stereogenic center because it has only one. It has only one substance. That's methyl repeated twice. Okay, now let's look at this second one. Okay, let's look at the second one. The second one could have been a stereogenic center. Don't forget that each of these edges in a cycloalkane, each of these edges actually have 2 hydrogens, but they are not usually indicated. Are you getting what I'm saying? Now we have only one methyl here, so that means plus the other hydrogen attached, so that means one of the hydrogens has been replaced by a methyl here. So if we extend this to put an hydrogen here, so that means we have 2 different substances, an hydrogen and a methyl. So you can see that an hydrogen and a methyl. All right. So if you have an hydrogen and a methyl, so that means it can possibly be the stereogenic center, 2 different substances. Now let's start tracing the parts. So let's say okay, let's start tracing the parts. 1, 2, 3. So you can see that on our first carbon we have methyl. We have 2 methyl here substituted. So 1, 2, 3. Oh, sorry. So if we take this one as 1, 2, 3, 4. Okay. So that's on our first carbon. We have on our second carbon here that we have 2 methyl. So if we trace from here now, so this is our 1. Don't forget, we are using it as our reference point. Then 1. Oh my. So 2, 3, 4. So you can see that on our fourth carbon, that's where we have the 2 methyls represented. So that's telling us that the parts are actually different. The parts are actually different. So I hope you get the logic there. So the parts are, so that means this place is our stereogenic center. Okay, now let's move to the in order to understand better, let's move to 1,1,3 trimethyl cyclobutane in order for us to get it better. All right, so in the 1,1,3 trimethyl cyclobutane, so let's look at it. We have 1 here, so 2, 3. Now this number 3 could be is the one that could be our stereogenic center. Please don't mind the numbering. I shouldn't have numbered it this way. Okay, since we are making reference point to our stereogenic center, so that means I should have named it, numbered it as 1. All right, so let's go look at it here now. So like we did before, that we established that there is an hydrogen beside that. So the same way, so if there is an hydrogen, that means it is attached to 2 different substances. So that means a methyl and an hydrogen. So now let's start counting. 1, 2, 3. You can see that we have a substituent at the 3rd carbon here. 3, then 4. Right. Now let's move to the other direction. 1, 2, 3. So you can see that in both directions, our movement is at the 3rd carbon. Are you getting what I'm saying? Our movement is at the 3rd carbon. So as a result of that, so that's simply telling us that this cannot be, it cannot have a stereogenic center. So it doesn't have a stereogenic center because the directions are still the same. So that's that. Okay. So lastly, we have limonene. Now for our limonene, let's say what could we possibly have as stereogenic centers. Let's look at this fourth carbon here. It could possibly be our stereogenic because it is attached to two different substances, so hydrogen and the other group here. Yeah, all right, so two different. Now let's start taking our part around it. 1 2 3 4 5 6. So I want you to take note of where it is substituted, where we have our double bond. 1 2 3 4. So we have 4 here. So 5 6. So our double bond is at carbon, is at this carbon here. Can you see? So that's after we move. So 1 2 3 4. So we move just 4 times. We go to our carbon. So the same way, when we move let's move to the other direction. 1 2 3. 1 2 3. You can see that we just moved 3 times, and our double bond we already find it substituted. Unlike here that we move 1 2 3 4. Can you see, before we meet our double bond? So that means the directions are actually different. So when we measure it along the stereogenic center, so you can see that. So that's how to find your stereogenic centers for ringed compound. So I hope you were able to learn from the video. So kindly subscribe and share. Thanks.